Okay, guys, here's a solution for the exam. I'll get into more details as you guys work through this, okay? So it says here, the following questions will be graded on a scale of 1 to 4, and points will be awarded based on your response. Told you guys, the responses, the better the response can be, the higher your score is going to be. So we're going to go ahead and start solving these questions one at a time. And the expectation is that you're doing it on yours and taking notes, okay? So it says, identify the trend that you see on the graph to the left. Okay, well, this is really simple. If you look at the 3 graphs that you guys were supposed to make, okay, you should have been able to recognize, because you have them in your notes, that this one is the trend of the periodic trend, atomic radius versus atomic number. That's all you had to put for this one. Super, super easy, okay? Question 1A says, label both axes of the graph and identify the peaks and valleys with the element names, okay? Right here, identify. When I say identify, guys, if I ask you to identify yourself, do you say boy or girl? No, you say, hey, my name is, Ernesto. My name is, Jenny, whatever. So when I ask you to identify these, is you're supposed to circle them, right? Here are the peaks. Okay, and here are the valleys. Now, if you did all of them, that's okay. But really, I'm just looking for like ones that really stand out the most. Okay, looking at the periodic table, we should have seen that this is lithium, this is sodium, right? This is potassium. Okay, and then the valleys, these are all the noble gases, guys. You see, looking at the periodic table here, here's helium, here's neon, here's argon, right? And go all the way through. That's basically all that you had to do. I ask you also, guys, to label the axes. So this should have been as simple as putting atomic number here. And then over here, atomic radius. Okay, that's literally all you had to do for this question. This question was worth 1 point. This question was worth 1 point. This one was worth 4 points. And this one was worth 4 points. Explain the trend you see represented here and justify the pattern across the period. What is happening at the atomic level that we see this pattern happening? Okay. So one thing I want to make sure that we get across, guys, is a lot of you guys gave me answers like, well, I see the period is, really high at 1 point, or like the graph is really high at the peak, and then it goes down to the valley, and then it repeats peak, valley. Basically giving me a rundown of what's happening on the graph. Guys, I can see what's happening on the graph. You need to tell me why this pattern emerges. You need to explain what we see happening across a period. Okay, so look, if this is lithium and neon is down here, okay, this represents a period. You can't see it here, but there's hydrogen here. Okay, so this is period 1, this is period 2, and this should have been labeled on your notes too, because when we did the Socrative on this, this is exactly what I asked you to do. This is period 3. Okay, so from the start of a period to the end of the period, we see that the trend, and believe it or not, a lot of you guys said that the atomic radius was increasing. The trend is that we see the atomic radius decreasing from the start of the period to the end of the period, okay? So explain the trend represented here, justify the pattern, and what is happening at the atomic level. Okay, so let's write a response. I'm gonna scroll this down a little bit. Let me see, where's my, oh, here we go. To my other page right here, and I'm gonna enter the text box. Okay, so I'm gonna enter question. This is 1B, I believe. Okay, the trend represented is the atomic radius versus the atomic number. Starting at period 2, from lithium to neon, we see that the atomic radius, oh, typos like crazy. is gradually or steadily decreasing period. Okay. I don't know how that happened. Decreasing across the period. Okay. As we move from left to right across a period, we are increasing the atomic number. The atomic number represents the number of protons and electrons. As more protons are added to the nucleus within the same energy level, and this is optional, right? But you can say that the electrostatic attraction from the protons to the electrons increases. Okay, now you can say the electrostatic attraction, or you can just say that the attraction between protons and electrons becomes greater. And as that becomes greater, the nucleus pulls in, my goodness, pulls, I did it again, the electron cloud closer. Yeah, sorry guys, trying to think and type at the same time here. Okay, so simple way to explain this is that the trend represents the atomic radius versus the atomic number. Okay, starting in period 2, from lithium to neon, we see that the radius is gradually decreasing. Okay, as the radius decreases, what's happening is we're increasing the amount of protons in the nucleus. As the amount of protons in the nucleus increases, okay, what we're seeing is that the pull from the electrons, or from the protons to the electrons, becomes greater, and the protons or the nucleus pulls in the electron cloud just a little bit tighter and constricts it. Now, I know I've said this in class several times, and that should have been in your notebook, because when we did the Socrative, we explained that. Okay, so this response here addresses everything that I asked. I didn't have to write a novel, okay, but it says explain the trend, all right, across a period. All right, it's decreasing. What's happening at the atomic level is we're adding more protons to the nucleus. What we see is the pattern emerge is as you increase the number of protons, the nucleus constricts. And as you go down the periodic table from one period to the next, we see an increase in shells, which results in a larger atomic radius. Okay, that's it. You don't have to write me a page and a half. You just have to explain it in a way that lets me know you understand what you're seeing. If you're giving me an explanation of what the peaks are doing, I can see that. You need to tell me why they're doing that. Question C says, provide a general statement about the trend you see in how it increases or decreases across the periodic table. Well, from what we see here in the period, using my mouse here, okay, we see that across the period here, it decreases. Okay, and as you go down the periodic table from one period to the next, we see an increase in the radius, right? So if I was to provide a general statement about what's going on here, okay, let me see here, add another text box, see if I can do it without so many typos. Okay, atomic radius increases down the periodic table from period to period. Across a period, we see that radius decreases as you move from left to right. That's it. That's it. Atomic radius increases down the periodic table from period to period. And across the period, we see that radius decreases as you move from left to right. General statement explaining exactly what this graph is showing you. Okay. Again, didn't need to write a novel, didn't need to to form an entire page of a solution. You just need to explain it in a concise way, right, in complete sentences, what it is that we're seeing on the pattern that we're exploring. Okay. All right. Question number 2, what is the first ionization energy of an atom? This definition you should have had in your notes. Okay, I had a few people that actually just copied it straight from the notes. I prefer that you use your own words, right, to give me the definition. But if you put the definition from your notes, I give you full credit. Ionization energy is the energy required to remove an electron from the valence shell. That's it. That's all it is. Okay, we did this with the tug of war. Okay, that's how you answer question number 2. Question number 2A says, to the right, we see the trend of first ionization energy. What pattern emerges as we move across a period? Okay, same thing again. Okay, this here is, let me get my drawing here. This is hydrogen. This is helium. When we start over here, this is lithium. And as we go to the end, this is neon. Right here is sodium. And as we get to the end, this is argon. Okay, so if I'm looking at a period at the periodic table of elements, I can see that this here represents period 1. This here represents period 2. This here represents period 3. And as we go from the start of a period to the end of the period, what are we noticing about the trend in ionization energy? The trend is increasing. We have an increasing trend in ionization energy. So I'm going to put first IE. Now, that's not going to be enough to give you full credit, but you have to be able to recognize if you're describing your trend as, well, it's a zigzaggy pattern that goes up and down. All you're doing is telling me what you're seeing on the graph. You need to tell me what it is that's happening with this periodic trend to show that you understand it. So to the right, we see the trend of the first ionization energy. What pattern emerges as we move across the period? Okay, so as we move across the period from the beginning, for example, lithium to neon, what we see is we see a steady increase in the first ionization energy. To paraphrase, we can say that the energy required to remove an electron gradually gets harder or gets higher as you move across a period towards a noble gas. Okay. Why do we see this? Well, as you get more and more electrons to filling up your orbital shells, then the desire to keep electrons begins to outweigh the desire to lose them, right? Which is why elements here in this area are going to reduce, and elements here in this area are going to oxidize, right? Because depending on the level of your subshell, being full is going to determine whether or not you're going to either pick up or drop off electrons. But that's all you have to say, right? Is a simple statement saying, as we move across the period, we see that the ionization energy gradually increases and becomes really, really high at the noble gases, all right? All right, 2A, on the graph, find and circle the following elements. So beryllium and nitrogen. So let me get my circle here, beryllium. Can I zoom in here? Let me see if I can zoom in here a little bit. There we go. Okay, so here's beryllium. Okay, and here is boron. All right, here is nitrogen, and here is oxygen. says, using the electron configurations and orbital theory, justify why we see a decrease in the ionization energy at either one of these points. Okay, so here's what it's asking you, right? I had you circle these two elements, and you can see that from this element here to this element here, or from this element here, which is beryllium to boron, we see a slight spike in ionization energy, and then we see a drop, okay? The same phenomenon happens at nitrogen and oxygen. Here's nitrogen, okay, and here's oxygen. So it's asking you, why do we see this pattern? Why do we see a slight uptick in ionization energy, and then we see a downstroke in ionization energy from one element to the next? Now, it tells you explicitly here, it tells you use electron configurations, okay, and orbital theory to justify your conclusions, right? And it doesn't say you have to do all of them. It says you can either do one or the other, okay? Now, here, let's take a look at the ionization, or let's take a look at the electron configuration for beryllium, okay? So 1s, 2s, 2p, okay? So this is beryllium. Okay, let's take a look at boron, okay? 1s, 2s, 2p, okay? All right. So let's take a look at beryllium first. Get the red one. So this guy has an ionization energy of 1s, 1s2, okay, and then 2s, 1, 2, right? Okay, let's take a look at boron. Here is the electron configuration for boron. Okay. Based on these configurations, right, can we see why one would have a higher or slightly higher ionization energy than the other? Okay, well, if we look at beryllium, beryllium has a 2s orbital that's already full, right? We have a full subshell in the 2s orbital. 2p orbital is completely unoccupied. So what we're seeing here is, even though the entire energy level is not yet full, sorry guys, even though the energy level is still not yet full, what we're seeing here is that at the very least, we have a fully occupied subshell in the 2s, right? All right, when we get to boron, right, we see this still has a full subshell here in the 2s, but now we got that one lonely electron out there in one subshell in the 2p. Right? So because it's got that one extra electron, it's going to act like those group 1 metals that have that one valence electron in the outermost shell, and it's going to just not want to keep it. So when you go from boron, right, to beryllium, I mean, from beryllium to boron, you see this one electron in this totally empty subshell occupying one single space, right? And that right there is the reason we see a slight drop in ionization energy, because the atom is not going to fight as hard to keep that one extra electron in a almost totally empty 2p orbital, right? Just take it. I'd rather have a nice full 2s and not worry about that extra one. When you take a look at the configuration, for example, in oxygen and nitrogen, you see the same thing. Okay, so here's your 1s, here's your 2s, here's your 2p. Okay. So let's take a look from nitrogen. So it's going to be 5, right? So 1, 2, 1, 2, 3, 4, 5, right? Right here, the 2p is still not full, right? It's still not full, but at least every subshell has an electron. Having an electron in every subshell creates what we call like an orbital balance, which makes it slightly more stable, right? So even though the 2p orbital is not completely full, at least all the subshells in the 2p orbital are occupied, right? So because that happens, all right, here's the 2s, here's the 2p for oxygen, right? Because that happens, oxygen is going to be in the same boat as boron. It's going to have that one extra electron right there that's going to screw up all the balance, right? It's going to screw up all the balance, all the symmetry, and the stability. So it's going to dip in ionization energy, okay, just to get rid of that extra electron that's kind of throwing things out of whack, all right? I know we've gone over this too, but this is how you justify your answer using electron configuration and explaining exactly the phenomenon that you see on the graph presented to you guys, okay? Okay, this is how you're supposed to answer questions, okay? Don't describe to me what you see on the graph. I can see that too, guys. You need to tell me why those things are happening. All right, identify this element. All right, so this already tells me it's gonna be in the 4th energy level, okay? I can see that because of the 2, it's gonna be in the D block. So this is 4th energy level. Remember, guys, go by energy levels and not periods, okay? Certain periods exhibit several energy levels, okay? So you need to understand which energy level you're working with. This tells me that it's a d orbital element, okay? So we know it's in the d orbital. Okay, it has a +1, okay? So if this is my d orbital, 1, 2, 3, 4, 5, it's gonna be -1, -2, -1, 0, +1, +2. So what this tells me is that in the d orbital, it's going to be in this subshell. And this guy right here tells me that it is a fully occupied orbital because it has a positive and a negative spin for the electrons. So let's go ahead and fill in the electrons. 1, 2, 3, 4. Okay, so now I'm in the correct subshell, right? But I know it can't be this electron because this subshell is supposed to have both a positive and a negative spin electron. So then I'm going to keep going and fill it up. 5, 6, 7, 8, 9. This is my electron, right? This is my electron because now I have a full subshell at the +1. I'm in the 4th energy level, okay? And I'm a d block orbital. Remember that d orbitals always exist one energy level lower than the period. So if I know that because the d orbitals are one energy level lower, then I know that this element exists in the 5th period in the d block, right? In this subshell, the element must be silver. Must be silver. Okay, that's how you do those. All right. This one was worth, this is worth 2 points. This one is worth 2 points. This is worth 4 points. This is worth 4 points. Going up here, this was worth 2 points, 4 points, 4 points. You get graded based on your answer of how many of those points you've earned for the question. So providing this, the silver would have given you the full 2 points. Justifying it the way I did here would have given you, again, full points. This was just a straightforward question. For the element above, provide the corrected shorthand or noble gas configuration. Okay, so you had an option to do one or the other. Okay, so to answer question 2A, I'm going to do this in black now. To answer question 2A, okay, this is the video that I told you guys that if you wanted to get an A, you needed to watch and you needed to understand, because I explained this exception in the video. If you didn't watch it, then you had no idea what I was talking about. Okay, so silver has this, I'm going to just do the configuration here of the row that it's in. So it's going to be the 5s2, I mean the 5s, and then the 4d, 2, 3, 4, 5, the 4d. Okay, so this is the configuration. Actually, I have it here, right? But I'm going to do the full one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so when silver, right, and there's 2 groups that have this exception. I explained this in the video. Silver, which is in group 11, and manganese, which is in group 7, have this exception. Okay, not manganese, sorry, chromium, group 6. So when we have a configuration like this, where the d orbital is that much closer to being full, right? What it does is it borrows this electron from the s orbital and puts it here, right? And what that does is it gives it a much more stable configuration because now your d orbital is completely full, right? So if we were to do the shorthand configuration of silver, right? If I look at the, let's see, it's going to be krypton. The configuration for silver would be krypton, right? If I'm going to do the shorthand, the noble gas, it'll be 5s1, 4d10. where this orbital is completely full. Okay, and this is the exception that I explained to you guys in the video that you were supposed to study. But again, that was optional. If you gave me the configuration that we see here, you got about half credit. You got about half credit. So of the full 4 points, you would have been awarded 2 points, provided, of course, that you had the correct element to begin with. Okay. Let's see. Make sure to include all possible oxidation states and justify as to why it forms these ions. Okay, so we just answered 2A. Let's go to 2B. Okay, so because silver has this adjusted, let me erase this guy real quick, has this adjusted electron configuration, then the only thing that's really left, right? Let me erase this here, is this electron. Okay, so this is now the electron in the highest energy level. So highest energy level electron. Now, the reason that this is now the lone highest electron in the energy is because now the D block is completely full, right? So because the D block is completely full and it doesn't really want to get rid of those and throw off that balance and that symmetry again, it's really going to only oxidize just this one electron. Now, remember, and this is also something that I explained in that video, that when you're looking at metals, right? Specifically transition metals, okay? They still have, because they exist, they start off in this 5s energy level, like in this in the 5s shell, they still have this empty 5p orbital, right? So metals will tend to oxidize more easily because they don't want to have to go through the trouble of filling up this one plus these 6 more electrons, right? Especially when this is already full at the 4D. So when silver ionizes, okay, silver is going to oxidize this electron here, right? It's going to oxidize this electron. And it's really going to only oxidize this one. Now, there are several possible oxidation states, but the most common ones, and you have a reference table in your notes that goes into detail on this, is going to be that silver is going to form a +1 ion. Silver is going to form a +1 ion because it only has that 1 electron to oxidize. So in your explanation, right, what you're going to write as your explanation, you're going to say silver is going to oxidize 1 electron because the 4D orbital, since it's full, right, is not going to really release or oxidize any other electrons, you know, for orbital stability. Since it only has 1 electron in the highest energy level, silver is going to oxidize that 1 electron in the 5s. And since it's only oxidizing 1 electron, it's going to end up with a net +1 charge. The ion that forms as a result is a +1 cation. Okay, is +1 cation. That would be sufficient to get you all 4 points for that question. Okay, again, if you didn't watch the video and you didn't prepare for the exam, then this question kind of confused you a little bit. Okay. Question number 4, final question. What is the compound? What compound would form if this ion bonded with a phosphate ion? Make sure to show all work and provide the final compound in the answer. So let's write a 2C here. I'm trying to squeeze it here just to kind of give us as much space, but you know what? Now that I'm thinking about it, let's just go ahead and scroll down. Okay, so silver forms a +1 ion. Okay, phosphate forms an ion, is an ion with a 3- charge, right? I didn't ask you to name this, I just asked you to form the compound. So when dealing with ions that are polyatomic, you're going to treat these guys as a single element, right? Even though they're made up of more than 1 atom, because they're ions, they're not going to change. You treat them as a single element, and then you figure out how these charges end up at 0. So right now I have 1 - 3, right? So that does not equal 0. So what do I need to do to balance these guys out? Well, in this case, what I'm going to do is I'm going to multiply. Let me erase this real quick. I'm going to multiply this guy by a 3, and I'm going to multiply all this by a 1. Okay. When I do that, I'm going to end up with silver. That's it now because I multiplied it by 3 is 3 plus. Okay. Phosphate, I'm going to multiply it by 1. So that stays exactly the way it is. That's a -3. 3 - 3, ding, 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 We get 0. So to form this compound, I'm going to write silver phosphate with a 3 next to the silver. Silver phosphate. Okay. Again, I did not ask you to name it. I just asked you to give me this compound. If you want brownie points, you can write it as ions, which is silver, right? With no, with a charge of +1, bonded 3 of those with 1 phosphate. All right. Either way, it's the same thing. All right. Shortcut, if I have silver, that is a 1+. Sorry. Say 1+, and then I write a +3. Okay. And phosphate, which is a 3-. If I take this number and I bring it down here, and I take this number and I bring it over here, right? See how it makes like a little fish? All right. Then I get the same compound. The 1 is out here, but since the 1 is understood, you don't have to write it, and you end up with the same compound. Okay. All right, guys, that was it. That's all you needed to show me to get full credit on that. I showed you about 2 or 3 different ways to do it. But what I want you guys to take away from this is that you need to understand the material. Okay, you need to be able to explain it and show that you've learned it. Okay, and the way I did this exam here demonstrates that I have a firm grasp of the material. That's where you need to be, especially if you're looking to get a good grade on these exams. Okay, what I want you guys to do is I want you guys to go ahead and add these notes to your exam in Google Class, and we'll go ahead and we'll talk about it. All right.